Hi everyone, I am Ritojit Kundu, a PhD student at IIT Kanpur, and I am one of your TAs in the course of Advanced Quantum Mechanics with applications. So today we are going to discuss about week 1's assignment. So I'll mostly be giving you some hints so that you can complete all of the problems, and I'll also be covering some other problems which are really important for fundamental concepts. So without further ado, let me share my screen, and let's start the discussion. All right, so let's first discuss the assignment problems. So I have chosen few assignment problems which I think is important and needs some basic understanding. So I'll be covering those first. So let's first look at the assignment problem 2, which asks you to calculate these cross products. Okay. So but normally when you do a vector algebra, so we know that if we do a cross product of a vector with its own, then the resulting vector is 0. But this case may not be true for quantum mechanical operators. So in the case, so like when we do this 0, so we assume that okay, a times some ax times ay is same as ay times ax, because these are just numbers, and numbers always commute. Okay. But in quantum mechanics, if we replace those components with operators, then this might not be the case. Okay. So in the same spirit, you can start by writing the L vector in terms of its three components. So like Lx I cap plus Ly j cap plus Lz k cap, and you can just do the cross product like you do like L cross L. Okay. So then just do I j k and just do Lx Ly Lz and Lx Ly Lz. So you have to remember that all of these Lx Lys are now operators, and they generally don't commute. Okay. So now if you will finish this thing, so you will get three components of this vector. So one in I cap plus something in j cap plus something in k cap. Okay. So then you have to match these quantities with with the right hand side of the equation, like Lx I cap plus Ly j cap plus Lz k cap. So if you correctly calculate this cross product, you will see that the resulting components will satisfy relations like this: Lx Ly commutator bracket is equal to I h bar Lz Ly Lz is same as I h cut Lx, and Lz Lx will be same as I h bar Ly. So these three commutation relations will come from if you solve this equation. Okay. So let's move on to the next one. Okay. So I mean, as I mentioned, just please remember that for normal vectors, so this was the condition. Okay. But not for quantum mechanical operators. Alright, so let's move on to the next problem. So let's look at problem 3. So here a particle is trapped in an infinite potential well in one dimension of width L. If the particle is in the ground state, evaluate the probability to find the particle in the interval 0 to L by 3, L by 3 to 2L by 3, to L by 3 to L. To solve this problem, first of all, what we need to know is the wave function. Okay. So in generally, let's say we know some wave function psi x. So if we know the wave function, then this actually gives us the probability density. So probability density is psi x then mod square. So this is the probability of finding the particle between x to x plus dx. Okay, so this is the probability density. Okay, so if we this is probability density, but if you multiply dx with it, then it becomes a probability. So this is right now the probability. So probability density is just psi x mod square. So now if we know the probability density to find a particle between x to x plus dx, right? So we know the probability of this part, like, so this is my x and this is my x plus dx. So we know what is the probability. Okay, so this is given by psi x mod square. So now let's say somebody is asking, okay, what is the probability to find the particle between x1 and x2? So what will happen is, so we know for each of the slices, like we will make a lot of slice, okay, and we will know the probability for each of the slices, that probability density times that dx of that slice. Okay, so true. And then what should we do is we should do a total sum of all of these slices, so then only we can find the total probability of the particle being found in x1 to x2 interval. Okay, so this so what I'm saying in mathematical language, it translates to something like this: x1 to x2 dx. So this is the probability of finding the particle between x1 and x2. So now the task which is left is you just plug in all of those values, like the first interval 0 to L by 3 as your x1 and x2, and you can plug in L by 3 to 2L by 3, right? And you can also plug in 2L by 3 and L. Okay, so just plug those things in this expression, and you know that as the question mentioned, has the particle is in the ground state, the psi x in this case is given by 2 by L square root and sine pi x by L. So this is your wave function in the ground state, and you use this expression, okay, and you find you calculate the integration to find the probability to get the particle between these points. Okay, so I'll leave this integration for you to do, and I'll then move on to the next problem. Okay, so problem 5, again consider a one-dimensional infinite potential well of width L. So the wave function is given by psi x0 is equal to 3u1 and u2. So the u1 is the first ground state, so it's a ground state, and u2 is the first excited state. So this wave function is given at time 0, that's why this 0 argument is there, and this u1 and u2x are normalized. So u1 and u2x are normalized means what? This means that if you calculate so like this u1x and u1x u1, so let me write like this. So u1x mod square integration over dx 0 to L will give you 1. So this is what this is the meaning of the normalization, and this is the same for u2x mod square also. So this is what normalization means. So now this u1 and u2 is normalized, but the psi x0 is not normalized. Okay, so in quantum mechanics, the first thing you should look out whether if wave function is normalized or not So in case it is, if it is not normalized, then you have to normalize it before doing any calculations. So as the first question suggests, let's look at how to normalize this. So psi x 0 is written in terms of 3u1x plus 4u2x. So I will just add another a factor, right, so that I can find that a factor for which this wave function will be normalized. And then what I need to calculate is psi x0 mod square okay, so let's just leave for now, and then we'll again start with the same link. Okay. Okay, so again let me share my screen. Yes. Okay, so we are calculating the normalization psi x0 mod square. So so to normalize it, we'll have to make sure that this quantity 0 to L dx is equal to 1. Okay, so then how do you do that? So you just calculate this thing 0 to so you just calculate this thing, and because this u1 and u2 are normalized, so that's why it will just become a mod square and 9 plus 16, and then it should be equated to 1. Okay, and we will find the a for which this is normalized. So this is a is nothing but 1 by 5. Okay, so this a is equal to 1 by 5 is a normalizing constant. So the wave function, normalized wave function at time t, is given by 1 by 5 times 3u1x plus 4u2x. So this is what the normalized wave function is. So you can find the average energy and momentum of the particle. So finding the average energy is also very easy. So this is part A. So finding the average energy is also pretty easy. So let me just arrange this thing a little bit. All right, so so let's see how do you find the energy. So to find the energy, you have to calculate the expectation value of the Hamiltonian, okay, over this state, over this normalized state. So you just put the psi, normalized psi, in this, and so you just calculate psi x 0 star h and psi x 0, okay, and do the integration from 0 to L, and you are done. So actually the action of h on this psi is very easy. So let's calculate it separately. So action on h is so nothing but, so the h will go through the numbers and it will directly act on the states, because h is a linear operator. And for same for this u2 part also, h will directly add to the u2x. Now we know this this u1 and u2 are the eigenstates of this Hamiltonian. So then it will just give you numbers e1 u1x plus e2 u2x. Okay, so this is how the Hamiltonian acts on this thing. So then when you will plug this thing and do this integration, and you will use the orthonormality property of u1 u2, then you will see that this thing becomes 1 by 5 times 9 e1 plus 16 e2. So this is the total expectation value of the energy. Now in a similar way you can also calculate P average. Okay, so now the part let's do the part C. So part C says that what is the psi xt. So psi xt is given by e to the power minus I h t acting on psi x0, and it will act on each of these wave functions, and it will give you the time dependencies e to the power minus I e1 t u1 x plus 4 e to the power minus I e2 t u2 x. So this is what the time dependence will be of the function. Okay, so now as you know this psi xt, so then you can also find the density psi xt mod square for part D, and you can also integrate over the regions 0 by L by 2 like we have done in the last problem. You can do it like that to find the probability, okay, for different times. So this is again our probability density. Okay, so I'll leave that for you to do, and I'll move on to the next problem. Okay, so in the problem 7 you are asked to find the boundary conditions in this case. So the potential on the left hand side, on the left is infinity, and on the right beyond x is equal to a, this is 0, and in between this is minus v0. Okay, so there are clearly three regions, region 1, 2 and 3. Okay, so in region 1 psi x is 0, psi 1, let's call it psi 1 is 0 because v is infinity. Okay, so there cannot be any particle in that region, so there psi is 0. So in region 2 psi will obey, psi 2x will not be 0 because the potential is finite and it will have some nature. Okay, it will not be 0 generally, and in 3 also it will not be 0. Okay, so how do we match the boundary condition? So at x is equal to 0 we will do x psi 1 0 is equal to psi 2 0. So that takes care of the boundary condition here. Okay, so psi 1 0 is psi 2 0, and at x is equal to a, then there are actually two conditions. So you will first have to match the values of the wave function at that point. So psi 2a is equal to psi 3a, and there is also d psi 2x dx x is equal to a, and d psi 3x at dx x is equal to a. So you have to match both of the values and the derivatives at the other boundary to get the solutions. Okay, so this will give you some linear equations, and you will solve them to find out all of the constants of this differential equations. So okay, let's move on to the next problem. So the next problem asks you to find the 0-point energy of a harmonic oscillator. So the harmonic oscillator, for harmonic oscillator we can write the Hamiltonian, which is given by h is equal to p square by 2m plus half m omega square x square. Okay, so 0 point energy refers to the ground state energy. Even if the particle is in ground state, it has a finite energy. So this is what they are asking to find, but we not using the normal calculation that we do, but using some heuristics and Heisenberg's uncertainty principle. So let's calculate h expectation. So h expectation will be p square by 2m plus half m omega square x square. Now because the harmonic oscillator has this symmetry, the harmonic oscillator is actually a function of x square, and it is actually even. So that's why so we can actually write this in terms of the uncertainties in the delta p and delta x also. Okay, so let's first write delta p. So let's write delta p square. So delta p square is p square average minus p average square, and delta x square is delta x square average minus x average square. Okay, so now this is the important property that because of the symmetry of the symmetry okay, okay, so let me just create another link because their link is yeah, it is just problematic. Okay, so let's start with the problems again. Because of the we are talking about the symmetry. So because of the symmetry of the wave function x average is 0 as well as p average. Okay, so these quantities are 0, and we are only left with the p square average and x square average. So you can clearly see, instead of p square average, I can directly write delta p square by 2m plus half m omega square delta x square. So here we will use the uncertainty principle. So uncertainty principle is it tells us that delta p times delta x should be greater than equal to h bar, h cut by 2. So we'll be taking the equality here, okay, the lowest the lower bound of this inequality, and we'll be using this to substitute delta p as h bar by 2 delta x. Okay, so then the expression has only delta x square, and it becomes 2m by h bar square by 4 delta x square, and there is the rest of the part. Now we want to find delta x, for which H expectation is minimized. So this the minimization problem, how do we find the solve this problem? So first we have to take the derivative of this energy with respect to the d delta x, okay, with respect to delta x, okay. And to find the minima, we'll first solve this, 0, and that will give us some x, some that will give us some delta x star, for which h is minimized. And so we'll plug this in the expression h, okay. So then you will see that it will directly give you some energy which will be h bar omega by 2. So you see, by doing so little we have already obtained the ground state energy of the Hamiltonian. So let me just repeat these parts. So h is just p square by 2m plus half m omega square x square, and this delta p square is nothing but p square average minus p average square, and so is true for delta x square. So because the symmetry of the ground state, or of the wave functions, what will happen is the x average and p average will be 0, and we can directly replace, instead of p square we can directly replace with delta p square. So now we will be using the uncertainty principle. So we will be using the lower bound of uncertainty principle on this inequality, and we will use it to substitute delta p in terms of delta x. So right now our the energy is fully in terms of delta x. So now we want to find a delta x for which the energy is minimized. So this is a minimization problem, to solve which we use we take a derivative of the Hamiltonian to the delta x, and we solve for delta x, okay. And then when you solve for delta x, that gives us a special delta x prime for which the h energy is actually minimized, okay. So then we will use this delta x and we will just plug this back in our h expectation. So that will exactly give us the h bar omega. So I have not done the steps from here to here, from in this steps, so please do the algebra. Okay, so let's move on to the next problem. So the next problem, it talks about so what the first excited states of the particle in simple harmonic oscillator is given by this. So you can look at this and you can see that this is actually an odd function x. So now you are asked to calculate the delta xp and delta x and delta p. Okay, so before jumping into calculation, let's try to do some symmetry arguments and see that which thing will be actually non-zero. So delta x square is x square average, as you know, minus x average square, and delta p square is also p square average minus p average square, okay. And so you can argue that so you can see that the x average is 0 and p average is also 0 because of the symmetry. Okay, so but this x square and p square are these will not be 0 generally. So just so you don't have to calculate these two parts, like you don't have to calculate this and you don't calculate this, because this will be 0. Okay, so you just focus on calculating the x square and p square average part, and you will be done. Okay, so it is a good idea to always look for symmetries before jumping into the full-fledged calculation. So, and you can eyeball a lot of things, like you can eyeball a lot of things to be 0. Okay, so this was the I think the last problem that I wanted to discuss from the assignments. So please do the assignments and submit before the due date. So other than this assignment problems, I have also noted down some problem which I think that might be interesting and which is important for concepts. So in quantum mechanics, we normally talk a lot about this linear operators. Okay, so first of all, Schrodinger equation is actually a linear equation. Okay, so if this was not a linear equation, then the superposition principle will not hold, which is just a property of the linear differential equations, and all of the superposition that gives rise to different properties will also not be true, right? So and most of the operators that you will see in quantum mechanics will be linear. So you should identify whether an operator is linear or not. Okay, so the definition of linear operator is given by this. Like, I have an operator which acts on let's say this kind of a function. So this is a linear combination, so there is a and b, which are just numbers, and there is f and gx, which are some functions. Okay, so this is when you act some operator on this combination, so the action of a linear operator is like it goes through the numbers and it goes and directly acts on the functions. So like it goes through a and it directly acts on g, and on the second term it goes through b and it acts on g. Okay, so a and b in this case are any general complex numbers. Okay, and so I have given you some linear some operators, and I am asking you, can you identify whether these operators are linear or not? So first let's have a look at some of this. So let's say that let me solve the problem B. So problem B is, so the O2, so I'll be taking this O2 and I'll be acting this O2 on a linear combination of shies. Okay, let me take a combination like this. So you are free to take any combinations that you want, chi to x. Okay, a and b are again complex numbers, so let me write it here. A, b belong to complex numbers. Okay, and the chi's are the chi 1, chi 2 are square integrable functions, so which is denoted by L2. Okay, so the action of this thing is, so it gives you a x ddx times chi of x okay, times a so a chi x, chi 1 x plus b chi 2 x, and so you know the operation of this thing. This actually doesn't act on the numbers. This will go through the numbers and it will directly act on the functions. X ddx chi 1 x plus b x ddx and chi 2x. Okay, now we can recognize this part. So this, the x ddx is nothing but O acting on chi 2. So again we will write in terms of O2 again. So O2 chi 1 x plus b O2 chi 2x. Okay, so now you see we have started from here, and we have represented in terms of the actions on individual functions. So this is actually linear. So let's do another example. So like, let's do the example D. So example D, so in example D, so O4 is given for on some chi x is just e to the power chi x. Okay, so this is the operation, and let's try to see whether this operator is actually linear or not. So again I will take a linear combination of functions. So a chi 1 x, so you are free to take your own combination for this. This is arbitrary, up to your choice. Okay, so So the action is like whatever this O4, whatever it acts on, it just takes it to the exponential. So it will be a psi 1 x plus b psi 2 x. Now so the exponentials property is that we can actually break it down: a psi 1 x and e to the power b psi 2 x. Now so the in the exponentials we can actually do a little bit simplification, so that it becomes to the power a times e to the power psi 2 x to the power b. So now we recognize these two parts. So this is nothing but O acting on psi and O acting psi 1 and O acting on psi 2. So we'll write in terms of O only. Okay, so let's do that. So now this one becomes O psi 1 x to the power a O psi 2 x to the power b. So you see that we cannot reduce it further, and we can put in a formula like 1. Okay, so this is actually not a linear operator. Let's check another one out. So let's check this operator C. This is interesting, and this kind of operator is encountered in many cases, okay, in quantum mechanics. So O3 acting on psi, so the action is it gives you some number times psi x star. Okay, so let's try to see whether this operator is linear or not. So I'll again start with our favorite linear combination, and the action is clear that it will give you some number and it will make this whole thing conjugate. Okay, so psi a1 becomes conjugated, psi 1 becomes conjugate, b star and psi 2 star. Okay, so now what we can do is we can actually get the lambda inside. Okay, like this: a star lambda psi 1 star x plus b star psi lambda psi 2 star x. Okay, so now again we understand these parts, and these parts are nothing but a star O3 acting on psi 1 x plus b star O3 acting on psi 2 x. So you see that it resembles the linear operators form, but it is not actually linear because it is making those numbers complex conjugate. Okay, so this is actually not a linear operator. So O3 is not a linear operator, but this operator has a special name. This kind of operator has a special name, antilinear operator. So this actually so there is an example of antilinear operator is time reversal operator. So there is an operator that you will learn later on in quantum mechanics, time reversal operator. Okay, so this is one example of an antilinear operator. So yeah, so I have done some of the examples, so I'll ask you to do all of the other examples. So there is an interesting example, interesting operator O6, which is like some integral operator, and the action is like that. So I'll ask you, so this is important, you try to do this, and so I'll give you the answer first. So this is actually linear operator, you try to show that this is a linear operator. So when you have proven all of these things, you can actually calculate the commutators, okay, to get a practice of how to do the commutator algebra. Okay, so this is a very good practice, so please do this algebras. So another problem which I have in mind is so what are the eigenstates of the symmetric potential well? So we have done a potential well which is actually not symmetric and which goes from 0 to a, right? So the symmetric so it goes from 0 to a. Okay, so for this, you know, the solutions are only 2 by L, okay, 2 by a in this case, square root sine n pi x by a. Okay, but if we make this if we do a let's say change of reference and we go from minus a by 2 to a by 2, okay, so then what is the psi n? So my question is, what is the psi n? Okay, so actually for this problem you don't have to do a lot, you don't have to solve the whole Schrodinger equation. You can actually start from this equation and you can do a change of basis of, let's say, change of reference. Okay, and don't have to solve. To start from Schrodinger. Okay, so how do you do that? So, and one thing is that the energy so the energy is same for both of these cases when the well is from 0 to a and it is from minus a by 2 to a by 2. So energy doesn't change. So okay, what is the change of reference that we want to do? So the change of reference is like we want to make sure that x goes to x minus a by 2. Okay, so that the origin is shifted by a by 2 in the negative direction. So we'll assign this variable to y and we will just write x is equal to y plus a by 2. So we'll plug this back in, let's call this 1. Okay, so plug this in 1. Okay, so then what we will get is psi in x is 2 by a and sine n pi x by a. So I am again okay, so let me write it a function of y by y plus n pi by 2. Okay, so we can use the law of sine a plus b and we can break this apart. So this becomes sine n pi y by a cos n pi by 2 plus cos n pi y by a and sine n pi by 2. So you see that this might seem a little complicated, but when you consider the cases like when n is odd, then this cos so okay, when n is odd, then cos n pi by 2 this becomes actually 1 and this becomes actually 0. So like cos pi by 2 is 0, cos 3 pi by 2 is 0. Okay, so in that case your psi n in that case, okay, so I'll write that later, but so let me write the other case when n is even, then sine n pi by 2 is actually 0. So these are the two conditions. Okay, and these are the two conditions, and you see that so in whether it is even or odd, only one of this term actually survives. Okay, so So there can be an additional minus sign in front of the signs, in front of this sign or cosine, depending on what is this n, okay, whenever they are non-zero. But the overall sign actually doesn't matter in quantum mechanics. So whenever you add an overall sign to the states, the expectation value actually doesn't change. So overall sign or overall a phase transfer, phase multiplication is trivial. It doesn't do anything to the observables, to the expectation values of the observables. So let me write down this answer. So psi n x, so there are two cases. So one is square root 2 by a, square root 2 by a cos n pi by a, okay, and in another case square root 2 by a sine n pi by a. So this is for n is equal to odd, and this is for n is equal to even. So you can sketch some of the states, for example. So let's do for the n is equal to 1. So this is my potential well, and this is my this is my origin, and this is my n is equal to 1. Okay, so for n is equal to 2, let's draw with a different color. So for n is equal to 2, it will be something like this. It will be a sine. So this is for n is equal to 2. So for n is equal to 3, it will be again a cosine. So as it goes on in the number, this number of nodes will actually increase. Okay, so this is how you should do that. And now so this is, you see, the interesting thing about this is that right now the system is in a symmetrical manner, and we are exploiting the symmetry. So whenever you exploit the symmetry, then the problems at hand becomes a lot simpler. So now the cosines and sines has a definite parity. So that means that cosines and sines are even and odd respectively, right? Okay, so I missed a x here. Okay, all right. So cosine and sines are these are just these even and odd functions. So you can clearly calculate this x averages. So x average for all of these things will become 0, okay, from the symmetry of the wave function. And p average will also become 0, so just from the symmetry, right? We are in a symmetrical coordinate, and we will be exploiting this thing. Okay, so here also you can try to calculate this p square average also, and x square average also. So this will not be 0. Okay, this will have some value which will, because for uncertainty principle, this cannot be 0. Okay, so uncertainty principle imposes that this doesn't be 0. So if you are done with this, then we can actually look at a complicated operator. So you can go ahead and you can try to see this thing. And I mean, so I will emphasize this case that before writing, starting to write down all of these operators, these are complicated operators. So you first try to understand, is this going to be 0 or not? Okay, so from any symmetry argument, if you can argue that okay, this thing will be 0, then you save a lot of calculations and a lot of pages, right? So so I'll encourage you to do that. Okay, so you try to see that whether what is the expectation value of this operator. Okay, whether it is, first check whether it is 0 or not. Is there a symmetry argument from which you can justify your answer? That is good enough. Okay, you don't have to do additional calculations for that. So all right, so this is the last problem that I wanted to discuss. So the problem, it tells you that at t is equal to 0, the particle is known to be localized on the left half of the box. Okay, so so this is the initial wave functions form. Okay, and this only resides in the first half. Okay, it is not in the second half. Okay, so now the first question is, what is the probability that an energy measurement yields ground state energy, and will the particle stay localized for later times also? Okay, so so when these kind of questions are asked, so first you write the wave function that is given in terms of the eigenstates of the system. Okay, so the general principle, so let me start with the general principle. So general principle is so the wave functions, the eigenstates are complete. So uh, so that means if the eigenstates are defined in the domain, let's say some a to b, okay, some these are some points, or let me write it like x1 and x2, then you can uh, you can resolve any square integrable functions, or let's say any functions in terms of the eigenstates. Okay, so that means that the functions in the eigenstates in, like again, x belonging to x1 to x2. Okay, so the eigenstates like, so any function we can always write in terms of Cn and psi nx, where the n summation is over all of the quantum numbers. So this is a very general principle. And how do we find Cn? So to find Cn, we will just multiply this whole thing from the left with a psi m star x. Okay, so then here also Cn psi m star psi m star x psi n x, and then we'll be taking an integration over this thing, over the whole region. So like in this case I am calling this x1 to x2, x1 to x2, and dx and dx. Okay, so now so we know that this wave functions are eigenstates are orthonormal. So that means that this quantity will give you a Kronecker delta m comma n. Okay, so then there will be Cn summation over n. Okay, and this is this quantity on the left hand side will remain as it is, psi m star x f of x. All right. So now you know that it's a Kronecker delta. So this makes it non-zero only for the case when m is equal to n. So we can do a summation over n, then that will give us Cm. Okay, so Cm is given by x1 to x2 psi m star x f of x. Okay, so this is the way you find a you find this Cn's. So let me write in a separate box. So Cn is given by x1 to x2 and psi m star x psi n x dx, or not psi n x, f of x dx. And the Cn mod squares is the probability of finding the particles, the particle in the state n, right? So this is a very important principle, and you please try to remember this. Okay, So now we can actually jump into the problem after we have understood this part. So okay, so all right, so now we know that our psi our this psi x0 0 is given in terms of 2 by a square root. Okay, so when this is in the first half, x is between 0 to a by 2. Okay, and it is 0 for otherwise when x is greater than so x is a by 2 to a. Okay, so this is the two cases. So first I want to resolve this psi x0 into the this eigen states, right? So Cn psi in x. Okay, so how do I find Cn? So Cn is given in terms of, so because of this is partly in the box, so 0 to a and psi in x and psi x 0. Okay, so now we can plug in the psi x0. So psi x0 will give you non-zero only up to a by 2. So the integration becomes 0 to a by 2, and there is no other part. Okay, so psi in x, and this is just 2 by l. Okay, 2 by a. So now, so we can plug in the psi in x. So I'm missing a dx here. 0 to a by 2, so then there will be 2 by a square root in sine n pi by x and a. Okay, and then this is, there will be additional 2 by a. So this will give you 2 by a, right? And then you have to do the integration of sine from 0 to a by 2. So then the integration will give you actually minus cos n pi x by a divided by n pi by a. Okay, so and the limits are from 0 to a by 2. So then this will be 2 by a times a by n pi, and then there is cosines, for which I have to first substitute the values. So minus cos n pi a times a by 2. Okay, and there will be a minus and additional minus that will make it plus. So then there is 1. So there is a and a which will cancel down, and so this will become, so I'll also cancel a and a from here. This is 2 by n pi, and this is 1 minus cos n pi by 2. Okay, so so now you can calculate this quantity, and you will see that for odd n, okay, so this might depend on the what is the n. Okay, so this is basically my Cn. Okay, and if you know the Cn, so the Cn mod square will tell you the probability of being in that state. So so now the question asks that what is the probability that this energy measurement will give you in the ground state energy, right? So then for this you calculate C1 mod square. Okay, and so now the next question is, will the particle stay localized for the later times? So and you cannot tell for sure, but you can do the calculation. Okay, so after you have known all of the Cn's, then the psi x0 is written in terms of this Cn psi n x0. Okay, and the time evolution, like we have done before also, is given by Cn e to the power minus I ent by h bar psi nt. Okay, so this is how the time this is how it evolves in time. So you can see, you can check out for later times. Okay, for t greater than 0, the wave functions smears out. Okay, so think about this, think about does it localize again? In the future? So yeah, so this will be it from my side for today. uh, so I'll see you in the next week, and these notes that I have written today will be available to you, and also the video recording of this session will be available to you, so for your future references. Okay, so please do the problems and try to have a look at these problems also. So I'll see you next time.